So this is the question number 7. We have two different temperatures for the boiling point of nitrogen and oxygen, which is the mixture content of air mostly. So as the if we have a really cool down air, let's say the air is cooled down, so cooled down that the whole air is now liquid, and if we allow the temperature of that liquid air to increase at 196 degrees Celsius, one gas will start to boil, one element will start to boil, and that element is nitrogen. Nitrogen is going to keep on boiling for this duration. That's why the temperature is going to remain constant, because that's what happens when state change occurs. As long as the state change occurs, the material maintains its temperature and it absorbs latent heat. So we are providing heat, but that heat is used as latent heat. So for this duration, nitrogen is gonna be boiling. When nitrogen is done boiling, then the temperature will start increasing once again. And when the temperature reaches 100 minus 183 degrees Celsius, then oxygen will start boiling. And then the temperature will start going again. So what you can see over here in these two parts, that this is the boiling scenario for nitrogen, this is the boiling scenario for oxygen. They're happening at two different temperatures. And this is basically how, this is one of the, this is not basically, this is one of the ways how we can extract pure nitrogen and pure oxygen out of thin air. Just cool them enough, make it all liquid, and then you collect the nitrogen at a lower temperature, then you collect the oxygen at a bit higher temperature. Or if in another sense that I can tell you, if we capture some air within a, let's say, metal container, and if we start to cool it down by some cooling mechanism, and if we lower the temperature of that air mixture below minus 183 degrees Celsius, let's say we lower it to up to 190, not up to 196, we lower it up to minus 190, then obviously this would be below minus 183, which means the moment the temperature of that mixture is going to fall below 183 minus 183 degrees Celsius, oxygen is going to start getting liquefied. So you will see that in that whole chamber there was all gas. The moment we reach minus 183 degrees Celsius in the cooling process, you will start to have precipitated liquid. You'll see that liquids are starting to form on the walls of that container and they are dripping down. That liquid is liquid oxygen. So if you just use a tap to drain out the liquid oxygen and save it in another cool down container, then you can essentially capture liquid oxygen pretty easily. If you cool it even further, if you cool it all the way up to minus 196 degrees Celsius, that's when you are going to get liquid nitrogen. So this is one of the ways to do this. I'm telling you this stuff because so that you understand. I described this graph, both from lower to higher temperature, also for high to lower temperature. What's going to happen for the heating process, also what is going to happen for the cooling process. So in question number A, we have some theoretical question. I want you guys to try this. Try to think about the answer of this thing, and then I'm going to show you the mark scheme just after a while. I'm really interested that you try to solve this question, number B. You already know the two formula that we have given you. The formula for specific capacity is given by E equals to mc delta theta. That's for temperature changes. And the energy required for state changes is given by E equals to m into L. L can be LF for melting, we call it fusion, or it can be LV, which is vaporization or boiling. So এই দুটো equation use করে আমাদেরকে এই জিনিসটা so এই question, the question is asking us calculate the thermal energy needed to warm the liquid from this temperature to this temperature. So how much energy would be required to achieve this? I want you guys to try this right now, and then I'll help you solve this. If you cannot, try karo, I'll give you some time. I'll pause the recording because this is a blank time. Try this problem. Within this temperature range that the question is asking us to calculate the required heat for, none of these liquids is undergoing any state change. Both of the liquids are liquid. So we can apply the formula E equals to mc delta theta for both the liquids individually. But because we have two liquids, we have to go for two calculations. So let me write this one. Let's say total energy would be equals to energy required by nitrogen plus energy required by oxygen. That can be written as mass of nitrogen into his specific capacity of nitrogen into delta theta. Delta theta is same for both of them. That's why I'm not using a subscript over here. I'm only giving a simple delta theta plus mass of oxygen into specific capacity of oxygen into delta theta. And now what you need to calculate is how much is the delta theta over here. How much did you get? 9 degree? এটা তো পারছো
9 degrees.
Yes, sir.
তখন বাকি ভ্যালুগুলো এখন বসাতে থাকো। and important জিনিসটা হচ্ছে, if you have a look over here, this unit is given joule per gram per degree Celsius. So, and these masses are also given in gram. So So because mass is in gram and this unit also is in grams, so you don't have to convert into kgs. You don't have to convert into kgs. So you just place everything into gram and that will work out just fine. Mass of nitrogen হচ্ছে কত 800 multiplied by C of nitrogen হচ্ছে কত 2.0. দেখো এখানে তো these people have intentionally done one thing. They have given the information of mass information of liquid oxygen first and liquid nitrogen second, and the specific capacity they've given the specific capacity of oxygen first and the heat capacity of nitrogen later. No, sorry, never mind. I thought they messed up this intentionally so that liquids fall into some calculation error, but they didn't. But they might. এই হচ্ছে total calculation. This much calculation should give you this value 14,400, and this much calculation should give you 3060. You have to add this together to get the total amount of energy required for both the liquid states. Make sense so far?
Sir.
Let's try another problem which is a bit interesting in my opinion if you ask me. এটা তোমরা চেষ্টা করলে পারবা, সেটা হচ্ছে লিকুইড স্টিমের একটা প্রবলেম আছে। এই প্রবলেমটা আমার খুবই ভালো লাগে। এটা হচ্ছে এই কোশ্চেনটা। আচ্ছা, এই কোশ্চেনটা তো তোমাদেরকে পুরোপুরি দেখাতে গেলে আমার খবর হবে, সো মেবি আই শুড ফলো ট্রাই এ ডিফারেন্ট ওয়ে মেবি। এখান থেকে ডাইরেক্ট ইমেজ কপি মারা বসায় দিই। এই প্রবলেমটা সলভ করো 11 নাম্বার। আমি এটা পুরোটা তোমাদের দেখাই দিচ্ছি। Try to solve this one. This is a problem identical to what we had been in our last class, using the same two formula equals to mc delta theta and equals to mlf, but you have to understand what to use when. Try to solve this one. I'll give you some time. Water enters in an ice making machine and emerges as ice cubes at a temperature of minus 5 degrees Celsius. The melting point of ice is 0 degrees Celsius. So you have to understand that we are having water of 16 degrees Celsius dropping to first 0 degrees Celsius water. So this is water, slightly less thickness, maybe good water, and then we have water, and then 0 degrees Celsius water has to convert into 0 degrees Celsius ice. The reason I'm using a horizontal arrow is to give you what can I say, subtle idea that temperature is remaining constant. So this is the state change, and then 0 degrees Celsius ice should go drop to minus 5 degrees Celsius ice. This is the 3-step calculation that you have to do. The question says that calculate the total energy removed from 1 kg of water as it cools from 16 degrees Celsius, changes into ice, and then cools to minus 5 degrees Celsius. So they have already told you that we are having these 3 steps of change. Specific heat capacity of liquid water is this much, specific latent heat of fusion of ice is this much, and specific latent heat capacity of ice is this much. So we're going to be using mc delta theta for this part, we're going to be using mlf for this part, and once again mc delta theta for this part. But what is important, never mind. So what is important is that we do not mess up the specific heat capacity values for 2 different states. Have a look. Liquid water has one value of specific capacity, and whenever it converts into ice, it has a different value of specific capacity. So we cannot use the same C for both of these processes. So let me write this equation in a convenient form that might make sense to you. I'm going to write MW CW delta theta plus M into LF plus into C ice into delta theta.
স্যার আপনার নয়েজের কারণে আপনার কথা শোনা যাচ্ছে না।
কি ধরনের নয়েজ?
মানে বাস টাইপের, সেই দিন যেমন হয়েছিল ওইরকম।
এখন বন্ধ হয়েছে?
জি স্যার, আবার মাঝে মাঝে একটু একটু করে, এই যে এখন করছে।
That's weird.
স্যার এখন বন্ধ হয়েছে।
Okay. So এই দুটো equation হচ্ছে আমার these are the this three step is the these are the three steps for calculation. What you need to understand that this mass is same for all three of the processes. For the state, for the temperature increase of water, for temperature drop of water, for the temperature for the conversion into ice, and for the mass of ice, mass will always remain the same irrespective of state. State means its kinetic energy condition, but mass of an object is an unchangeable property of an object. So m can be taken common from here, but let's say I'm not going to take it common, just to give you a visual idea that how this calculation can be done. In this case, we are told that we have 1 kg of water, so mass is 1 kg, so I'm going to write 1. C of water is 4.2 10 to the power 3, so 4.2 into 10 to the power 3, and delta theta is 16 to 0, so here the delta theta is obviously 16 degrees Celsius, so into 16, plus 1 into 3.4 into the power 5, plus 1 into 2100, 2.1 into the power 3 into 5. So one of the things that you can also and if you do the calculation properly with all the brackets and everything, so that your calculator doesn't mess up the plus and the multiplication processes individually, so that you make sure of that. If you do the calculation properly, what you will always be able to do is to get the correct answer. In this case, the correct answer happens to be where is the correct answer? This is the correct answer. So the way the mark scheme actually works is that, have a look at it, understand the content or the breakdown of the mark scheme. It says that E or Q, students might use any of this symbol, equals to MC delta theta in any algebraic or numerical form. For example, if this is shown 4200 into 16 or 2100 into 5. So the concept of being able to idea of MC delta theta either in the equation form or in the numerical values form is going to score you 1 mark. It proves that you know this formula, MC delta theta. Then there should be 3 different values seen: 67,200 or 10,500 or 77,700 seen, or E or Q goes to ML or ML algebraic sum. So any of these 3 values seen, these 3 values are the individual values of these 3 steps individually. So any of these 3 values that we can find, and then you have to then you might score this mark. Or if someone doesn't mess up if someone is too bad at the calculation, they don't get any of these values and altogether don't get any correct answer. But even if they have tried the second equation, which is E equals to ML, if it is seen in algebraic form or in the equation form, then they're going to score this mark as well. Lastly, the correct answer is an A1 mark, for which you can score the full mark. So এই প্রসেসটা বুঝা গেছে কিনা, ক্যালকুলেশনটা বুঝা গেছে কিনা বলবান?
স্যার কোশ্চেন কিভাবে করতে বলছেন এটা বুঝিনি।
কোশ্চেন কি করতে বলছে?
ইয়েস স্যার।
ক্যালকুলেট দ্য টোটাল এনার্জি রিমুভড, কোশ্চেন এটা করতে বলছে। So think about it. You have some 1 kg of water that is at 16 degrees Celsius. You want to convert this into ice of minus 5 degrees Celsius. To make this happen, you have to pull out heat from this container, right?
ইয়েস স্যার।
How much heat do you have to pull to convert this from 16 degrees Celsius to minus 5 degrees Celsius for 1 kilogram of water? That's the question.
Correct, sir.
Beautiful. Any further question about this one? Anyone? If not, I'll give you another question, which is this one. Now, here we have a lot of question over here. So how can I actually place these two questions side by side? Can I? Maybe I can, or can I not? Maybe I can. Okay, let me put this one here and take this one out. Put it right here. Pretty close. Okay. I want you guys to try this question right now. Have a acha, এখানে তো সেম কোশ্চেনই দেওয়া। আচ্ছা, অ্যাকচুয়াল কোশ্চেনটা হচ্ছে এইটা। এইটা ট্রাই করো। Read the question. Figure 5.1 shows steam passing into a jug to warm up some cold water. In this question, you may ignore any heating of the atmosphere. Pure steam enters at 100 degrees Celsius and the jug initially contains 500 grams of water at 20 degrees Celsius. Eventually, the water in the jug reaches a temperature of 100 degrees Celsius. The specific capacity of water is 4.20 joule per gram per degree Celsius and the specific temperature of water is this much. What is this? Acha, never mind. I have to keep it selected. So, okay. Let me try to elaborate the content of this question for your easy understanding. Take a good look at the figure. What does the figure tells you? We have some cold water and we're gonna blow in steam into this water. So steam comes in at some temperature. Steam is not essentially 100 degrees Celsius. The minimum temperature at which steam তুমি তো খুলতে পারবা না, দিচ্ছ কেন? Pure steam enters at 100 degrees Celsius and the jug initially contains 500 grams of water. So the thing point is I'm making that we're gonna blowing steam into this water, and that steam is gonna come into contact with the cold water. And as the steam bubbles are gonna rise up, some of the steam molecules, not all of them essentially, some of the steam molecules are gonna lose their heat to the cold water, and they're gonna become condensate, or they're gonna convert into from steam. দাঁড়াও 1 minute. Never mind. So steam is gonna come into this thing, and as the steam bubbles are gonna go up, they're gonna come into contact with the cold water, and some of the steam molecules are gonna lose heat to the cold water, and in that process they're gonna become condensated, or they're gonna change state from gaseous state. They're gonna convert into liquid water. This question tells us pure steam enters at 100 degrees Celsius, and the jug initially contains 500 grams of water at 20 degrees Celsius. Eventually, the water in the jug reaches a temperature of 100 degrees Celsius, which means all the water is now at 100 degrees Celsius, about to boil. The specific capacity of water is 4.20 joule per gram per degree Celsius, and the specific latent heat of vaporization of water is 2250 joule per gram. Calculate the energy needed to warm 500 grams of water from 20 degrees Celsius to 200 degrees Celsius. So first of all, they are asking us how much energy will be required for this to happen. So this is actually not very difficult, because here we have the mass given. The question has already given us the, the question has already given us this value. This is the specific capacity of the water. So we can essentially go ahead and try to solve this problem. Very simple, that this is going to be E equals to mc delta theta. So just place all the values over here. This is 500 gram into 4.2 and then 80. 80 is the difference between these two things. Can someone tell me how much this becomes? Does it become this one?
It's 168.
So this many joules is the energy required to this much water. Then comes the next question. Have a look at this one.
Sir,
Yes.
sir, don't we need to convert 500 grams to kgs?
For this question, no. I'll tell you why. For this question, we don't need that. এই লেখাটা এখানে চলে আসছে somehow, because it was on the earlier page. Why can't I have this লেখা on this page? Can I lock everything? এত প্যারা কেন? আচ্ছা, আমি এই লেখাটা মুছে ফেলতেছি। আর লেখাটা থাকলে সমস্যা নাই। You can read the content. You should be able to read the content in Zoom. I'll tell you why. Because the question has given us the mass of the water in gram. Have a look. Mass of the water is given in gram units. Take a look over here. But the specific capacity is also given in gram unit, involving gram unit. Check this out. So whenever we're going to do mc delta theta, ultimately your expectation is to get the unit joule. So you're gonna get some mass unit over here, maybe gram. If it is gram, then C should, if C is given in joule per gram, then you can essentially cross them out. That's the whole point. And obviously there'll be degrees Celsius, and delta theta is gonna come as degrees Celsius. So if you multiply all three of this unit, gram and per gram crosses out, per degree Celsius crosses out. All that you are left with is joule. So if your units match, then you don't have to convert. Make sense?
Yes, sir.
Beautiful. In question number D, it says calculate the final mass of the water in the jug when its temperature has reached 100 degrees Celsius. What this means that whenever hot steam is gonna come out over here and cold water is gonna slowly start to convert into, and the steam is gonna start converting into water, the amount of water in this thing is gonna increase because some steam will be converted into liquid water, which is obvious. Now the thing is that we have to calculate the final mass of the water. So here's the deal. Let's say initially the water of the jug was 500 gram. Some of the steam, let's say some mass of the steam will be converted into liquid water and get added with this mass. Our question is, how much is this? Because in the process of condensation, some steam would be converted into water. So the total amount of mass of the water in the container will increase by a little. So to be able to sum this up, we first have to calculate this one. Now you have to understand that this is the amount of mass of water gained by means of latent heat given up to the cold water. So this is the state changed water amount. This water used to be in steam form. By losing heat to the cold water, this water has now become liquid water. So if you just use that same formula, E equals to M into LF, where this M is the mass of the steam. So we can essentially calculate that the energy that this cold water absorbed from the steam is the same amount of energy that the hot steam gave up. So try to visualize this, that hot steams are entering into the liquid. They are giving up their heat to the neighboring cold water molecules that used to be in the jug, and the steam is losing heat and the water is heating up. So as the water temperature is rising from 20 to 100, some steam molecules, not necessarily all of them, some steam molecules are converting into liquid water. So steam molecules are losing heat, water molecules of the jug are gaining heat, and because water the energy is conserved quantity, so given up heat equals to absorbed heat. So that's why the same amount of energy that we had calculated in option choice B, which was the total amount of energy required, 168.16800, this amount of heat that was absorbed by the cold water was essentially coming from the hot steam that converted into liquid. So this one equals to mass of the steam into 2250. And from here you can calculate up this value. Then you have to sum this with 500 gram, and that's your answer. Does it make sense? The idea of energy transfer. Balaban? Hello?
Yes, sir.
কার কোনো কনফিউশন বা কোশ্চেন?
আচ্ছা,
আমরা আরেকটা লাস্ট কোশ্চেন আজকে ট্রাই করি, because we have a little bit of time left. সেটা হচ্ছে এটা ট্রাই করতে, সেটা খবর হয়ে যাবে। এইটা এটা মানে এখান থেকে অ্যাক্সেস করলে সহজ হবে। আচ্ছা আমাদের এখানে ইয়া আছে, আচ্ছা এটা আর লাগবে না অ্যাকচুয়ালি। I want you to be able to try to solve number C. Attempt number C as best as you can, then I'll help. Take time. This question is actually not very difficult. This is a state change question. The only way this question can prove to be difficult for some students, for those who did not read the question thoroughly, and as a result of that they missed out this 16 section information. They saw the mass, didn't read the question, they just looked for numerical values. So they saw the 20 gram, they saw the latent heat of fusion, multiplied them and got the energy value. That's it. That is the only location where this answer could be mistaken. Pretty much. And the rest of the part is pretty simple. The seed capacity of the facility does not affect the answer to 1 because for this entire process, the temperature is not changing. So if temperature is not changing, E equals to MC delta theta is 0. So the product of the whole MC delta theta will always be 0. And number 3 says the icebox takes energy from the water at a rate of 30 watt. Estimate the time range. So this is very simple. Power equals to energy by time. You just place the values and you can calculate the time from. This is a very simple calculation. So that pretty much does the part for number C. Acha, tomorrow I'm gonna take a leave. It's 11:01. It's pretty late. Thank you for the late class. And tomorrow we're gonna talk about some timing issues, and we're gonna also continue the problem solving for this worksheet. Thank you very much. Allah Hafiz. Good night.